We live in a remarkable age, an era where the boundaries of time and space are constantly being redefined by the marvels of technology. Technology connects us in countless ways, weaving a complex web of interactions that span the globe. From the smartphones in our hands to the vast networks that power the internet, our world is more interconnected than ever before. This connection is possible because of the powerful synergy of three fundamental fields: electrical networks, computer science, and cryptography. Each of these fields plays a crucial role in maintaining the seamless flow of information and energy that we often take for granted. These fields may seem distinct, but they are deeply intertwined, working together in harmony to create the backbone of our modern society. The collaboration between these disciplines is what enables us to enjoy the conveniences of the digital age. Together, they form the invisible infrastructure that powers our modern world. This infrastructure is a complex and intricate system that operates behind the scenes, ensuring that our daily lives run smoothly. Electrical networks form the backbone of our power grid, providing the essential energy needed to power our homes, businesses, and industries. These networks are the lifeline of our civilization, enabling us to harness and distribute electricity efficiently. They enable us to transmit electricity over long distances, bridging the gap between power generation sites and consumers. This capability is crucial for ensuring that energy is available where and when it is needed. This intricate web of wires, transformers, and generators brings light to our homes, powering everything from our kitchen appliances to our entertainment systems. The reliability of this network is a testament to the engineering prowess that goes into its design and maintenance. It also powers the devices that have become essential to our daily lives. From the moment we wake up to the time we go to bed, we rely on a multitude of electronic devices that make our lives easier and more enjoyable. Computer science provides the brains behind our digital world. It is the driving force behind the software and applications that we use every day, enabling us to communicate, work, and play in ways that were unimaginable just a few decades ago. From the smartphones in our pockets to the complex algorithms that power the internet, computer science is the driving force behind the digital revolution. It is the foundation upon which our modern digital infrastructure is built. It allows us to process information, solve problems, and create new possibilities. The advancements in computer science have opened up new frontiers in fields such as artificial intelligence, machine learning, and big data analytics. Cryptography safeguards our data and communications in this digital age. It is the science of securing information, ensuring that our personal and sensitive data remains confidential and protected from unauthorized access. As we transmit sensitive information online, cryptography ensures that it remains confidential and secure. Whether it's online banking, private communications, or personal data, cryptography provides the security measures that protect our digital interactions. It protects our privacy and enables us to trust the digital systems we rely on. In a world where data breaches and cyber threats are becoming increasingly common, cryptography is more important than ever in maintaining the integrity and security of our digital lives. Think of a circuit as a path. Electricity flows through this path, delivering energy where it's needed. Circuits are the fundamental building blocks of electrical networks. They control the flow of electricity in a precise and predictable manner. Three main components make up the most basic circuits: resistors, capacitors, and inductors. Resistors act like gatekeepers, limiting the amount of current flowing through a circuit. Capacitors act like reservoirs, storing electrical energy for later use. Inductors act like coils, resisting changes in the flow of current. The interplay of these components creates a fascinating phenomenon called resonance. At a specific frequency, called the resonant frequency, a circuit can oscillate with maximum energy. This principle is used in various applications, from tuning radios to designing wireless communication systems. Imagine trying to water your garden with a hose. The water pressure and the hose's width determine how effectively the water reaches your plants. Transmission lines are like hoses for electricity, guiding the flow of electrical energy over long distances. Just like the water hose analogy, transmission lines have a property called impedance. Impedance measures the line's resistance to the flow of electrical energy. Matching the impedance of the transmission line with the impedance of the source and load is crucial for efficient energy transfer. When impedance is mismatched, reflections can occur. These reflections are like echoes bouncing back in a canyon. They can distort signals and reduce the efficiency of power transmission. Section 4, the language of computers. Computers are incredible machines. They have revolutionized the way we live, work, and communicate. From the simplest tasks to the most complex calculations, computers handle it all with remarkable efficiency. They process information at astonishing speeds, but they do so using a language far simpler than we might imagine. This language is the backbone of all computing, enabling these machines to perform a myriad of functions seamlessly. At their core, computers understand only two states, on and off, represented by ones and zeros. This binary system, though seemingly simplistic, is incredibly powerful. It allows computers to store and process vast amounts of data with precision and speed. This binary system forms the foundation of all computer operations. Every image, text, and sound you experience on a computer is ultimately broken down into these binary digits. It's a universal language that transcends borders and devices. To make sense of these ones and zeros, we use programming languages. These languages act as a bridge between human logic and machine understanding. They translate our complex instructions into binary code that computers can execute. These languages provide a set of instructions that computers can understand and execute. From creating simple scripts to developing intricate software, programming languages are the tools that bring our ideas to life. From low-level languages that closely interact with a computer's hardware, such as assembly and C, to high-level languages that resemble human language like Python and Java. Each serves a unique purpose. High-level languages are designed to be more intuitive and easier to use, allowing programmers to focus on solving problems rather than managing hardware details. They enable rapid development and are widely used in various applications. Programmers use these tools to create software, whether it's a mobile app, a web service, or a complex operating system. The principles remain the same. They write code that instructs the computer on what to do, step by step. The beauty of computer science lies in its ability to break down complex tasks into a series of simple, logical steps. This methodical approach ensures that even the most intricate problems can be tackled efficiently. This logical framework allows us to automate processes, solve problems, and create sophisticated software applications. From automating mundane tasks to developing cutting-edge technologies, the possibilities are endless. The language of computers is not just about ones and zeros, it's about harnessing the power of logic and creativity to shape the future. Section 5, computing machines from simple to sophisticated. Imagine a simple vending machine. It accepts coins, allows you to make a selection, and dispenses your chosen snack. This machine operates on a set of predefined rules, much like a basic computer program. Now imagine a more complex machine, one that can simulate the workings of an entire factory. This machine, called a Turing machine, is a theoretical model of computation that demonstrates the power and limitations of computers. Real-world computers, while not Turing machines, utilize similar principles. They employ a hierarchy of languages, from machine code to high-level programming languages, to execute instructions and perform complex computations. Section 6, the art of sending signals. Communication is an essential part of our daily lives, and understanding how signals are sent and received can help us appreciate the complexity behind the technology we often take for granted. Imagine shouting a message across a crowded room. The noise and chaos make it difficult for your message to be heard clearly. This is a simple analogy for the challenges faced in communication systems. The noise makes it difficult for your message to be heard clearly. Just as in a crowded room, communication systems must deal with various forms of interference and noise that can distort the message. Communication systems face similar challenges when transmitting information over long distances. Whether it's a phone call, a text message, or data being sent over the internet, the signal must travel through various mediums and can encounter numerous obstacles. To overcome these challenges, we use modulation techniques. Modulation allows us to encode information onto a carrier wave, which can then be transmitted more effectively over long distances. Modulation is like attaching your message to a carrier wave, much like a surfer riding a wave. The carrier wave helps the message travel smoothly through the medium, overcoming obstacles and reducing the impact of noise. This carrier wave can be modified in various ways, such as changing its amplitude, like AM radio. Amplitude modulation involves varying the strength of the carrier wave to encode the information, or frequency, like FM radio, to carry information. Frequency modulation involves changing the frequency of the carrier wave to encode the information, which can be more resistant to noise and interference. Noise, like the noise in a crowded room, can interfere with the signal. This interference can come from various sources, such as other electronic devices, physical obstacles, or even atmospheric conditions. To mitigate noise, engineers employ various techniques, such as error correction codes. These codes help detect and correct errors that may have occurred during transmission, ensuring the integrity of the received message, and filtering, to ensure that the received signal is as close as possible to the original message. Signal filters can remove unwanted noise and interference, allowing the true message to be extracted from the received signal. Modern communication systems rely on a combination of these techniques to provide reliable and efficient transmission of information. From satellite communications to fiber optic networks and wireless devices, the art of sending signals is a complex and fascinating field that continues to evolve. Next time you make a phone call, send a text, or stream a video, take a moment to appreciate the intricate processes that make it all possible. The art of sending signals is a testament to human ingenuity and the relentless pursuit of better communication.